This report looks into the future. With advances in technology, commercial flight takes on the challenges of a changing world. The search is on for new systems to provide for safer flight and better management. Aerodynamic advances are finding their way into new places, and they're coming from some unusual sources. Scientists work to understand composites and to fabricate unique metals. Engines are taking on a radical new look, and the potential for economical supersonic flight moves closer to a reality. All these changes are shaping tomorrow's airliner, and they're setting the stage for commercial aviation in the 21st century. Since commercial flight began, new technologies have been applied when they provided an economic payoff. The Douglas DC-3 combined advanced technologies to become the first profit maker for the airlines. Passenger comfort was a priority. A load-carrying metal skin was created from aluminum alloys. High-powered piston engines and improved aerodynamics boosted the plane's speed to 150 miles per hour. Passenger comfort and operating economics improved with the Boeing 307 Stratoliner. Cabin pressurization enabled the plane to fly above the weather, where the ride was smoother and faster. But performance took a big leap forward in 1952 when the de Havilland Comet ushered in the high-speed age of the commercial jetliner. And low-bypass turbofan engines made jet service quieter and more fuel-efficient in the early 1960s. But it took the 747 to make long-range and large capacity a reality. High-bypass turbofan engines provided fuel economy, and the wide body could accommodate 385 people in the new twin-aisle configuration. The wide-body jets attracted great attention, marking a maturity in cost efficiency. But rising costs soon prompted new designs.
With the advent of the oil crisis, the airlines wanted even more fuel-efficient operation. So Boeing looked at the latest technologies with respect to materials and engine efficiencies and flight dynamics to package that into what the customers now are buying in terms of 757s and 767.
In 1974, a new player emerged on the scene. Airbus began to evolve a family of new aircraft that also took advantage of the latest technologies. But with the low oil prices of recent years, Douglas Aircraft Company has felt no need to follow suit.
Really does not pay to develop a new airplane with all the new technology when fuel prices are low. So what we're doing at Douglas is develop our existing airplanes, the DC-10, the MD-80, by applying new technology in a cost-effective way to those airplanes.
Both Douglas and Boeing now use this derivative approach to selectively apply new technologies. In Europe, Airbus, the third major player, is doing things a bit differently. A consortium of European companies pool their resources to compete with the established U.S. airframers, each building separate parts for final assembly in Toulouse, France. With the all-new Airbus designs came the opportunity to apply new technologies throughout the planes, in aerodynamics, in materials, and structures. But nowhere is the new technology more visible than in the cockpit. Indeed, throughout the industry, the fast-moving field of avionics is changing the way man flies.
It's on.
The cockpit of a modern jetliner is complex.
Check.
Flight controls and yaw dampers.
They're on and check.
To help manage and simplify this array of flight controls, the computer is becoming an increasingly important member of the flight crew. Boeing's newest derivative, the 747-400, has been redesigned with an integrated glass cockpit, removing the need for the flight engineer. At their Everett plant outside Seattle, Boeing is nearing completion of flight testing and certification for the plane that can fly 7,300 nautical miles, the furthest of any commercial transport in the world.
We're going to do a typical flight out of Boeing Field today. We're going to head south, turn to the east, go back to the north side of Boeing Field and do a landing. The flight's about 20 minutes.
James Weitengruber is manager of flight crew operations.
Brake release.
He's in the 747-400 engineering simulator.
A little bit here. V1, VR.
The displays, such as the primary flight panel, simplify and present information using a few easy-to-read cathode ray tubes. Here, the attitude, altitude, vertical and airspeed, and heading, each previously a different display, are integrated onto one CRT. They've kept familiar controls, such as the column and wheel, while adding new capabilities, as in the computerized navigation system.
Our airplane is located right at the apex of this triangle. The two white dashes you see out in front are 30-second and 60-second predictors on where the airplane is going to be. The pink line or magenta line that you see here is our current route that we've entered in our flight management computer.
The flight management computer coordinates the navigation systems, constantly updating a real-time electronic map so the crew can see at a glance their location and route.
This is called ICAS, the upper and lower tubes. Engine information is provided on there. We also have the capability of displaying synoptics. An example might be fuel synoptic, in which we show where the fuel is located in the individual tanks, the pumps, where the fuel is flowing, the green mode that you see here, and the particular engines.
ICAS, the Engine Indication Crew Alert System, automates the monitoring of all the flight systems.
We reduce the complexity of this cockpit tremendously in going from a 3-man crew to a 2-man crew. Typical 747 would have around 1,000 lights, gauges, and switches in it. This airplane has less than a 767, slightly under 400 lights, gauges, and switches in it. Gears down.
Digital avionics are helping to reduce the pilot's workload
We have the automatics engaged.
and to make him more of a manager of the complicated flight systems.
10. And touchdown.
But the technology exists to go much further in computerizing the cockpit. The new Airbus A320 also has a digital avionics flight deck, but what's happening behind the displays is very different. 5 computers have replaced all the mechanical operations in this fly-by-wire plane. A side stick controls the flight surfaces by way of the computers, which send electrical signals over wires to the actuators.
Because the pilot is talking to a computer, we can tell the computer what the safe limits of the flight envelope are for the airplane. And if the pilot is trying to do something which is beyond those limits for whatever reason, then the computer can say, that's enough, you don't go beyond this point.
In a test flight, Gordon demonstrates how the computers stabilize the plane during a dangerous maneuver approaching a stall.
So here we go, I'll add on full thrust and pull full back stick and roll the airplane to 20 or 30 degrees of bank. So 3, 2, 1, go. Full thrust, full back stick, holding it. You see how rapidly the pitch attitude increased to 25 degrees. We roll to the bank angle that we want, but the speed and the angle of attack have remained totally in a safe range. And the airplane has, in fact, incredible maneuverability in this region, which is, as you saw, very close to the stall. We can prevent the pilot braking the airplane. He can't tear the wings off. If I'm doing 350 knots and I pull full back on the stick, the computer will take me to 2.5 G, which is the structural limit of the airplane, and stay there. We'll demonstrate now the overspeed protection system. I'll pitch the airplane nose down to a fairly steep pitch attitude, and I'll roll it to a reasonably high bank angle. You can see us accelerating. You'll hear the overspeed warning in a minute, which will stop when it sounds. I release the side stick, and we'll see what happens. Here comes the overspeed warning now. See the airplane rolling out on its own and pitching back up. The speed has stopped increasing. We've only in fact exceeded VMO by 12 knots. And you can see that the airplane is now climbing with the speed reducing towards the safe sector.
The fly-by-wire system controls all aspects of the plane's performance. But with computers augmenting the pilot's commands, does this change the experience of flying?
Every pilot that gets in it likes it very quickly. They're all a little bit nervous to start with because maybe they've never flown a fly-by-wire airplane, they've never flown a side-stick airplane before. But usually after 2 or 3 minutes, the guy will turn around and say, gee, this is wonderful. And not only that, but he says, you know, I don't feel as though I'm flying an airplane through a computer. I just feel as though I'm flying an airplane.
With these benefits, why don't all new planes use fly-by-wire controls? Like the 747-400, Douglas's MD-11, a DC-10 derivative now in assembly, incorporates digital avionics and a two-man crew, but not fly-by-wire. Why did they choose this design path when more advanced technology was ready for use?
It doesn't make economic sense to put all fly-by-wire controls in the MD-90 or the MD-11. The economic benefits are probably negative when you've amortized what it's going to cost you to put them in the airplane. You're not going to save fuel, maintenance costs, you know, just a little bit.
So long as Boeing and Douglas continue building derivative aircraft, the full potential of computerization won't be applied to the cockpit. Yet increasingly powerful computers are enabling NASA researchers to experiment with the cockpit of the future. Langley Research Center's Sam Morello envisions a flight deck with a new look.
The design is what we call a pilot desktop design. It enables us to bring some interface devices like the keyboard into the desktop design. So as the pilot becomes more and more of a manager, that he can do that through these interfaces, through a keyboard, maybe better through a touch panel capability on some of the displays that you see on the panel, or possibly through a voice input type of device. Here we see an indication of the aileron.
They've organized the systems visually as in the 747 and A320, but have added interaction with the computers through touch panels.
We can go back to the menu and also select the fuel system. Here he can look at the different pumps that are involved and choose to shut down or to engage pumps in that system.
Software switches replace mechanical ones that fill today's cockpit, even in the A320. And the computers even use artificial intelligence to help the pilot make decisions without throwing any switches at all.
We've developed an expert system called Fault Finder, and it will help the pilot as faults occur in the systems on the airplane. It will help him to determine which of the systems is at fault and make decisions concerning shutting down or changing his flight path due to those failures, and helps him at various levels in the types of decisions that we wish him to be making on the flight deck.
With this ever-increasing cockpit computerization, how will the pilot's role change in the future?
We fully intend that the human will be there in the cockpit in the next generation. There's obviously a lot of human judgment that can be applied by the human that we don't know how to reproduce in a computer yet, and probably won't be able to do that in the next 15 years.
But for the foreseeable future, the pilot is very much the decision maker in the cockpit, and new avionics are assisting him achieve more efficient operations and greater safety by reducing the possibility of human error. NASA Langley is testing a takeoff performance monitoring system as part of their Advanced Transportation Operating System. It may look as though the test plane is being piloted from within the conventional cockpit, but actually this 737 is flown blindly from a computerized cockpit in the passenger cabin. The takeoff performance monitor will be used to predict where on the runway important takeoff events will occur, and to indicate to the pilot the options he has for continuing or rejecting a takeoff.
Okay, we're ready to operate.
The goal is to prevent accidents such as the 1982 Air Florida flight which crashed on takeoff from Washington, D.C.'s National Airport. The tragedy might have been averted if a takeoff performance monitor had been available to warn the crew that icing had critically degraded performance. Another problem is the danger of mid-air collisions, one due in large part to increased air traffic. United Airlines and others are testing and using traffic collision avoidance systems, TCAS. Computer programs are hooked into the plane's transponder. The system interrogates approaching planes, fixing their position.
Traffic.
A display alerts the crew when an approaching aircraft is dangerously close and advises an evasive maneuver.
Advisory clear.
Though TCAS provides no economic benefit for the airlines, it does make flying safer. And Congress has enacted new legislation to make TCAS mandatory on most commercial transports by 1992. The challenge of avionics development is how to create new tools such as TCAS to increase safety and pilot capabilities without increasing cockpit complexity or crew workload. Technology development is aimed at gradual improvement in systems efficiency, while the application of all new flight controls must earn their way into the cockpit over the long term. Experiments with new mixtures of exotic metals and of revolutionary plastics is heralding a coming age of dramatically lighter commercial aircraft. Advanced aluminum alloys are being used in new planes such as the Douglas MD-11. The floor beams of the MD-11 are made of aluminum lithium, a metal that is being targeted for increased use.
We see a large interest in the aluminum lithium alloys. These are conventional aluminum alloys that we make aircraft structures from, but we've added lithium to it, like 1 to 3%. The lithium increases the stiffness and also the strength of the alloy, and it ends up saving about 10% in weight.
Douglas Aircraft Company is experimenting with new ways to form and stretch aluminum lithium alloys. These advanced aluminum materials yield modest weight reductions. It's an evolutionary and cost-effective use of metal in the airframe. The promise of a larger technological breakthrough, on the other hand, rests in the development of composite materials. At Boeing, composites are already being used in secondary structures on the new 747-400. The aerodynamic winglets are made of graphite epoxy composites. Carbon-carbon brakes replace steel, reducing weight and improving performance. Lightweight fire-retardant thermoplastics are used in the interior sidewalls, floors, and ceilings.
The fact that you can now blow mold or injection mold a material that replaces a part that might have 30 or 40 machine or sheet metal build-up parts means that for operating it and maintaining it and fixing it or changing it as they need to in airline service is of great value to the airline.
These operational benefits are combined with some weight savings, but they make up a small part of the 747's massive overall structure. The real challenge comes in stretching those savings by using composites in primary load-bearing structures.
We've come a long way in terms of aircraft structures. We now have non-critical structures flying today on aircraft that are made from a graphite epoxy type material. However, we've not brought that material along far enough to consider using it in primary structure, primary being like the wing and the fuselage. And those are the big payoff areas for the composite materials.
The big problem is designers understand how aluminum performs under stress. Composites, however, behave quite differently.
An aircraft structural designer really understands how to design a metal airplane. He's been doing it for 40, 50 years and longer, and really knows how to do that. He intuitively knows what the design rules are. We don't have those intuitive feelings now for composites, and we're having to go back and relearn the whole design process to take into account some of the particular characteristics of these systems before we can commit to something as important as a wing or a fuselage of a very large passenger carrying transport.
Starnes is conducting stiffener crippling tests on parts made of graphite and epoxy resins to shed light on their behavior. Instrumented test sections are placed in a compression cell and subjected to high loading.
Mark, this thing looked like it buckled about 20,000 pounds. What we need to do now is develop an analytical model that would represent all those interface stresses to the degree where we can come up with some kind of an estimate of what the actual critical failure stresses might be in that area there.
As composites are made of woven fiber layers, they can best withstand stress in the direction of the weave. New shapes must be designed that carry loads without the danger of delamination and structural failure. They're also testing how composites will respond to other types of stress.
Okay.
In an anechoic chamber, the acoustic response of composites to exterior noises is being tested. This composite fuselage will be subjected to propeller noises. First, though, they're doing tap testing to determine the natural frequencies to which the composites respond. Researchers can see how the cylinder reacts almost as a tuning fork does to various frequencies. The object of the tests is to learn enough about acoustic vibration fatigue to help predict the lifetime and behavior of composite aircraft structures. With this knowledge, NASA Langley scientists are creating stronger composite materials and developing innovative concepts that take advantage of their unique formability.
For example, this structure right here is one of the composite type structures that we would call innovative, which makes more effective use of graphite epoxy. This type of a structure we think would make a very good composite fuselage structure since it is very damage tolerant. It provides redundant load pass to carry the load, and it's also a very effective way to make a composite structure to put the fibers along the load pass where you really want them to be, and also it has the potential of being produced at a reasonable cost because this can be filament wound in an automated type of a process.
Reducing fabrication costs is critical. McDonnell Douglas is using composite wings on the AV-8B Harrier close support aircraft, but the hand layup of the thermoset materials is slow and expensive. Composite primary structures are still largely experimental, but commercial wings and fuselages may soon be getting a lighter ride from composite materials. In 1983, the American yachting team lost the coveted America's Cup for the first time in the race's history. They were beaten by Australia 2, whose hard-working crew also took advantage of advanced technologies to put distance between them and the American boat. Ironically, it was a creation based on NASA-developed aerodynamic technology. The secret weapon, kept well under wraps, was eventually revealed to be a winged keel. A pair of fins sprout horizontally from the keel, their unique design helping to improve the keel's efficiency in the water, which translates into faster speeds and improved stability. When positioned on an aircraft wing, as on the 747-400, the winglets provide the effect of increased span without actually lengthening the wings themselves. They improve lift by controlling the eddies or vortices which form at the wingtips. Because they allow greater range for the same fuel, winglets are becoming standard on new long-range transports. The Americans came back strongly in 1987 to win back the America's Cup. And once again, their hard work and skill was augmented by an aerodynamic advance developed by NASA. To reduce drag on the yacht's hull, thin transparent sheets of riblet film, manufactured by 3M, were applied to the stars and stripes. They discovered that turbulent water flow could be reduced by actually making the hull surface rougher rather than smoother. The riblet film is made of tiny striations which channel the flow down the ribbed valleys so that boundary layer turbulence is pushed up and away from the surface. This concept of reducing drag actually originated in nature. John Enders, NASA Langley.
Certain sharks have a structure, a skin structure, very similar to a riblet structure. You look at these things under a microscope, they're tiny V-shaped grooves aligned with the flow of the right scale according to our wind tunnel experiments to reduce drag. Only the fast sharks have these, the slow sharks do not.
Riblet film has the potential for reducing drag on commercial transports by up to 8%, which will result in lower fuel consumption. Another advance that's taking off will reduce drag even further. Laminar flow control could lead to a whole new wing design. On a normal wing, a thin layer of turbulent air builds up next to the surface, causing friction and drag. New wing gloves are being shaped with extremely smooth surfaces to allow the air to flow with less friction over the wing. On an F-14, NASA is testing these laminar or smooth flow gloves, mounted here on the right-hand wing. Liquid crystals help contrast the types of airflows. The hotter turbulent flow, seen in the blue, is being pushed back by increased laminar flow, identified here by the cooler green areas. More effective but complex flow control devices can be built into the wing. In a system Douglas designed, the leading edge is perforated with millions of tiny holes. Suction is then applied from within the plane, removing the rough air through the porous surface and extending laminar flow further aft on the wing. Designers have tried to make active flow control feasible for some time. Douglas's John Morris.
I personally was working on laminar flow control in the late 40s, but we were never able to make it work on a practical basis. Two reasons. One, you have to make the wing extremely accurate to maintain this laminar flow, which we didn't have the manufacturing technology to do at that time. Also, there were a number of operational problems. For example, there are a lot of flies and bugs in the atmosphere. When you're taking off or in low altitude flight, these things tend to impinge on the leading edge and stick there like glue. And every time you have one of those impinging on the leading edge, it's impossible to maintain laminar flow behind them. So you get a lot of them on there, you don't get any laminar flow.
A NASA Jetstar flight tested the suction device with a variety of bug control concepts. In this design, a flap deployed from under the wing during takeoff shields the leading edge from insects. The flap also doubles as a leading edge slat to improve the lift of the wing itself. Laminar flow control may soon be off experimental jets and onto commercial airliners, which could reap fuel savings of up to 20%. And around the corner, technology that's shaping tomorrow's engines. The power behind today's commercial aircraft comes from the high bypass turbofan engine, a design which has evolved steadily since it was developed in the 60s. New engines like the International Aero Engines V2500 are designed with ever higher bypass ratios. The blades dominate the jet in a high bypass turbofan engine, as seen here in Pratt & Whitney's large thrust PW4000. A small amount of air entering the engine is compressed, burned, and expelled at high velocity. This energy is used to turn the large diameter fan at the front of the engine. The fan drives most of the incoming air around the engine core and expels it as the primary thrust. Unlike the older jets, this slow-moving airflow more closely matches the forward velocity of the plane, resulting in higher propulsive efficiency, reduced fuel burn, and lower noise. But now this bypass concept is being taken to extremes.
We're looking forward to launching the MD-90 program in the very near future, and it will be a program based on new ultra-high bypass propulsion technology, the so-called unducted fan, or the Cuisinarts, as people here call them.
Ultra-high bypass engines, or advanced turboprops, are the biggest change in propulsion since the turbojet. They use the same bypass concept of the turbofan engine, but replace the fan with very large unducted propellers to increase the bypass ratio by up to 10 times. Although turboprop jet engines have been in commercial service since the Vickers Viscount was introduced in 1954, the propellers reach inherent limits at high subsonic speeds. Flow losses on the straight, thick blades are too great above Mach 0.6, too slow for today's jetliners, which cruise at Mach 0.8. But advances in computer modeling and design enabled Hamilton Standard to design a revolutionary propeller that could perform efficiently and reliably at high speeds. The extremely thin and highly swept blades depend on advanced composites for their improved strength. As with conventional turboprops, thrust is controlled with variable pitch. NASA-sponsored wing-mounted flight tests aboard a Lockheed Gulfstream jet proved out the concept. But efficiency is lost in the swirling flow that's created by the single blade row. So, a counter-rotating blade configuration was designed to straighten the flow. Based on this concept, two commercial ultra-high bypass engines have been built. A Pratt & Whitney Allison design placed the blades on the front. But they opted to build the test engine with pusher propellers on the rear, suitable for aft mounting on aircraft. Aft mounting keeps the blades, a source of noise, behind the passenger cabin. To turn the blade rows, this engine uses a reduction gearbox as in conventional turboprops. But at General Electric, a different counter-rotating prop fan engine was built, called the unducted fan, or UDF. This model uses a new gearless drive system in which the blades are powered directly off counter-rotating turbines, which simplifies the system and reduces weight. When flight testing began with the aft-mounted GE engine on a 727, ground-level noise was a chief concern. But flyover tests showed that the UHB engine is as quiet as or quieter than turbofan engines. Douglas is testing ultra-high bypass engines on an MD-80, their production line transport with aft-mounted engines. The airframe designers found that unducted fan engines present unique challenges.
We realized that with significant change in the propulsion system technology, it brought with it some new technical challenges that really needed to be examined. And one of them was the particular noise characteristics of this new engine. They were quite different in the near field than anything that we'd had experience with before.
To test the effects of this new power plant on the aircraft structure, a DC-9 fuselage was placed in an anechoic chamber and blasted with UHB engine sounds. These tests showed no signs of fatigue in the structure. Douglas then took to the air to test both the engine performance and the interior cabin noise levels. Insulating materials helped to reduce near-field noise transmission. Instrumentation collected data for acoustic and performance analysis. With aft-mounted engines, cabin noise levels were found not to be a problem, and the unducted engine shows promise for realizing substantial benefits.
The fuel consumption of these engines is roughly 40% better than corresponding turbofan engines, and of course that translates itself into a lower direct operating cost for the operator. At the same time, it offers the opportunity for lower airport noise, so it's a double benefit of application of the technology both in the economic and the environmental area.
These benefits prompted Boeing to design the 7J7, a new rear-engine plane with unducted fan engines. But the program was shelved because the economics didn't work out as they had done for Douglas.
It so happens that we already had an airplane that had engine on the back of the airplane, and it was relatively simple, therefore, to apply that technology to an airplane we already had and get the gains in fuel consumption that the prop fan UHB engine offered. Clearly in the case of Boeing and in Airbus, who have wing-mounted engines on their airplanes, it wasn't nearly as easy to apply that technology to their airplane. They've really got to talk about an all-new airplane, and with low fuel prices, it's not really economically feasible to apply the UHB technology to those airplanes.
So the only economic way for the other companies to take advantage of UHB technology would be to adapt existing airplanes. But to replace engines on long-range aircraft, the unducted prop fans must be scaled up to impossibly large sizes. NASA's John Grenowick.
We don't know how to build unducted fast turboprops in a configuration that's installable on a wing-mount long-range aircraft. Therefore, we're led to putting a duct back around the rotor, a large diameter, thin, lightweight duct. And by doing that, we can still realize perhaps 2/3 of the efficiency benefit of the advanced turboprop.
Placing a duct around the rotor delivers higher thrust for a given blade size by reducing blade tip flow loss, but it sacrifices efficiency by adding weight and drag. So the concept will actually be less efficient than technology allows, but applicable to more planes. Throughout the commercial aviation industry, this type of cautious technology application is taking commercial aircraft forward in selective steps. The next big challenge in commercial flight, however, is to find how to dramatically increase the speed of air travel and still make it pay. Commercial supersonic flight has been a reality since the late 60s, but the market potential for this new way to fly was limited by necessarily high ticket prices. Today, demand is increasing for air travel to distant locations, and with it is coming a renewed interest in high-speed flight.
Never has there been a more exciting time to be alive, a time of rousing wonder and heroic achievement.
President Reagan, in his 1986 State of the Union address, expressed a vision for a new era of hypersonic flight.
And we're going forward with research on a new Orient Express that could, by the end of the next decade, take off from Dulles Airport, accelerate up to 25 times the speed of sound, attaining low Earth orbit, or flying to Tokyo within 2 hours.
But the national aerospace plane has yet to leave the drawing board. Even the research involves technologies that can't be developed by the year 2000.
What we're focused on in that program is an airplane we call the X-30. It's a research airplane. It's not a prototype of any practical airplane. We wouldn't expect it to go into production at some point. It's really to explore the expanding envelope of aeronautics that we're dedicated to moving into in the next century.
The single stage-to-orbit capability of such a plane is more suited for space payloads than ferrying commercial passengers. Challenging technologies such as cryogenic engines and metal matrix skins to withstand temperatures of 1,000 degrees Fahrenheit must be developed. Other countries are also researching hypersonic aircraft, such as Aerospatiale's AGV, designed to travel 3,100 miles per hour. Japan, Germany, and Great Britain are each developing hypersonic concepts, primarily for industrial payloads. The earliest attempt in the United States to build a commercial plane that would fly beyond the speed of sound came to grief over public concern for environmental issues. In other parts of the world, supersonic transports did get off the ground. The Soviet Union's Tupolev 144 failed catastrophically. But the Anglo-French Concorde has been flying reliably since 1969. Only 16 aircraft were built. Compared to subsonic transports, the plane is noisy, fuel inefficient, has limited capacity and range, and is expensive to operate. NASA's Jerry Hefner.
The Concorde was a technological success. It was not an economic success. It was an airplane for the rich man. It was not an airplane for the average guy to fly on. And what we're talking about is an airplane that flies twice the range with 3 times the number of people for 1/7 the ticket price. And that is a tough challenge.
The challenge is all the greater considering that NASA has little money to pursue a commercial supersonic transport program. Limited funds are being used to continue research on some of the most pressing environmental problems. Concern over sonic boom and exhaust emissions is even more acute today than it was in the 1960s.
This airplane cannot destroy ozone. It's not acceptable. So we've got to do the necessary research to ensure that the combustors on these engines do not put out emissions that's going to harm our atmosphere. That's a given. We can't accept any deterioration of the atmosphere. Second, we want this airplane to be able to fly supersonic over land.
To do this, the sonic boom must be reduced to acceptable levels. NASA is testing models in a supersonic wind tunnel to explore how the shape of the planform affects sonic boom. Air pressures building up on the planform may be reduced using aerodynamic tailoring. Data gathered here is used to create synthetic sonic booms on the computer to test how different sound pressures are perceived.
The sound pressures that's received on the ground from a normal aircraft, say a military aircraft, is typically in the shape of an N wave with a very sharp rise time at the beginning of the signature and then a decay over time and then a sharp spike on the end as well. Now what we're trying to do is to reduce the sharpness of that rise time and expand that out over time and reduce the higher frequency components in the sound pressure that is generated on the ground. And by reducing that high frequency component, then people's annoyance would thereby be reduced as well.
This is our anechoic test chamber. If you would just follow me in and have a seat.
Powell is conducting human subject testing at the NASA Langley Research Center's Acoustic Division.
Now, what we would like for you to do would be to listen to a number of these different sounds that we'll play over our loudspeaker system, and for you to simply make a mark on your scoring sheets as to how annoying these sounds would be to you if you heard them, say, 8 or 10 times a day.
With sonic booms created in the computer, the researchers test the effects of aerodynamic tailoring. With these results, they're going back to the computer to create planforms that produce the least objectionable sonic boom, while maintaining efficient performance. A new NASA configuration is aimed at achieving that balance.
This is a Mach 3 concept. It would carry approximately 250 passengers over a distance of 6,500 nautical miles. The concept would weigh approximately 700,000 to 800,000 pounds. As you can see, the nose in the planform is relatively blunt. This is done to reduce our sonic boom signature. We have a highly swept aero wing type of configuration, highly swept over the forward part of the wing for the supersonic cruise performance that's necessary. Outboard, the wing has a decreased sweep, which is necessary for our low-speed performance. It's relatively slender, very thin. This is done to actually reduce the disturbances as the airplane slices through the air at supersonic speeds. This is necessary for not only performance, but also in trying to reduce the boom associated with configuration.
This transport would be larger than a 747. Its structure is highly integrated, with each part affecting every other part of the flight operation. High speed increases drag. Drag increases fuel burn and surface temperatures. A larger fuel load increases total weight, requiring larger, heavier engines.
We must reduce takeoff gross weight, and there are a number of ways to do that. We have to work propulsion, aerodynamics, structures and materials, as well as flight systems. Each of those have a big role to play. Probably the greatest are in the area of propulsion and structures and materials.
The hot skin temperature, around 500 degrees Fahrenheit, of a Mach 3 transport means that advanced high-temperature materials will be used in the structure. At the Martin Marietta Laboratories, an experimental aluminum-magnesium alloy is being developed. Here, vacuum casting of the lightweight, heat-resistant alloy prepares the molten metal for material studies. To reduce weight, innovative structures can be formed, such as this titanium honeycomb sandwich made by Alcoa. But to make substantial savings in weight, advanced composites offer the greatest potential.
For that type of structure, in a composite sense, we would again use a graphite-type fibrous material that we could weave or put in some innovative structural concepts such as we illustrated for a subsonic transport, and we would impregnate that with a high-temperature polyimide type material. And then these materials would be certainly satisfactory for the high temperature. However, I think it would be quite risky to jump into a composite material like this for supersonic transport before we really have demonstrated the technology in the subsonic transport. The dichotomy is, though, for a supersonic transport to become a commercial reality from an economic standpoint, weight of the aircraft is critical, which may drive you to use a composite material like a graphite polyimide. You may not have any other choice to meet the economic regime.
Aircraft weight also dictates the size of the propulsion system required. It's a tricky balance to retain efficient enough operations to make a Mach 3 transport economically viable, while at the same time reducing takeoff noise and emissions. For example, new burner designs can lower flame temperatures in core combustors, reducing emissions. Yet the most efficient way to fly the engines is with a flame temperature as high as possible. In the variable cycle engine concept, a large air mass bypasses the engine during takeoff to mask the noise from the intense jet exhaust. Then it converts to much lower bypass operations for supersonic cruise. Although the concept reduces airport noise, its cruise performance has limited efficiency because, as with all of today's supersonic engines, engine airflow must be internally diffused down to subsonic speeds. One innovative engine design allows some supersonic flow. By enabling air to flow supersonically through the fan stage and the bypass duct, diffusion losses are reduced. Pressure ratios at the fan are increased and the overall design is simplified. Testing of this supersonic through-flow concept is just beginning.
We've never been able to operate a compression system with supersonic through-flow from the inlet through the blade rows. And this will be a first of that type of a demonstration.
NASA Lewis engineers are now building a scale fan rig as a proof of concept for the supersonic through-flow turbofan engine. Titanium blades have been precisely cut, and this rotor will be placed in a stainless steel axisymmetric or round housing. The shortened engine inlet will be added to the front of the fan rig, and the unit will be run in this supersonic compression cell. If the system can be made to work, supersonic through-flow can provide major payoffs.
This ends up with less parts, less complexity, and less cost for the fan section. That trades off in terms of total weight to the system of approximately a 25% reduction in total engine weight. And that, in terms of fuel burn, which is the real thing that we're looking at, gives us about a 20% reduction in fuel, and of course that makes the high-speed transports more economically viable systems.
The supersonic through-flow turbofan will be feasible at speeds up to Mach 3, but up to Mach 5, temperatures become too high for moving engine parts. At those high supersonic speeds, the challenge of developing a suitable propulsion system begins to look very different. This 1/3 scale square inlet under test in a supersonic wind tunnel at NASA Lewis is part of a system aimed at the Mach 3 to 5 range.
Most of the past studies on supersonic transports have concentrated on axisymmetric or round inlets in the Mach 2 to Mach 3.5 arena. And these are usually mounted on the aircraft on struts underneath the bottom of the aircraft. As we get up to Mach 5, these configurations no longer integrate well with the aircraft, where two-dimensional inlets like this do.
The square inlet can be attached directly to the underside of the aircraft's body. The plane actually becomes part of the inlet system, a sort of flying engine. This integration reduces weight and drag.
The propulsion system associated with this inlet would be what we call the over-under concept, where the over part is an existing turbine engine that could fly from Mach 0 up to about Mach 3, but then in the Mach 3 regime, the temperature gets too hot, and we have to close up that engine, and then we turn on the under part of the propulsion system, which is a ramjet engine to fly from 3 to 5. And of course, a ramjet engine has no rotating hardware associated with it. It's strictly a burner.
They will be testing the unique problems associated with square inlets, such as airflows that get caught in inlet corners, requiring complex air bleed systems. And a more serious problem is brought on by shock waves that form in the variable geometry throat area, which may cause what is called inlet unstart.
Inlet unstart is the situation where the normal shock that exists within the inlet behind the throat comes roaring out of the inlet, and this is a very traumatic experience, produces almost instantaneous large pressures on the inlet system, and reduces the thrust on that propulsion system to almost zero. We must be able to control that, trying to prevent it, or if we can't prevent it, at least control it so that we can recover from that situation without any violent maneuvers on the aircraft itself.
Such violent maneuvers would be a problem indeed for a commercial transport. A Mach 5 transport is on the verge of hypersonic flight, the far edge of possible commercial development in the next 20 years. These challenges are multiplied in the much higher speeds envisioned by the National Aerospace Plane. In the context of commercial flight, the question becomes how fast is too fast? What's the economic benefit of hypersonic travel? A NASA-sponsored study with Boeing and Douglas explored the options.
The scope of that study initially was to look at airplanes with cruise speeds between 2 and 20. And we all came to the conclusion quite quickly that going above Mach 5 didn't really make any sense at all. You're really saving very, very little time. Although you might be going Mach 10, you might only be saving 10% of the time compared to flying at Mach 5. And the technology challenges at Mach 10 are much, much greater than Mach 5.
In the low supersonic range, as with these preliminary U.S. studies, other nations are cautiously investigating new supersonic concepts. The French ATSF, for example, may carry 250 people at Mach 2 by the year 2005. But for now, these planes are only computer models on a TV screen. The viability of such aircraft will depend on whether designers can solve environmental challenges and still create a moneymaker for the airlines. With these types of changes in the offing, how will air travel actually change for the passenger? Will there be fewer delays? Will there be less congestion? As reliance on air travel grows, more planes will be needed to meet increased demand. Yet airport capacity is already stretched to its limits.
We suddenly find ourselves addressing issues that we probably didn't think we were going to address until well into the year 2000, and that's the need for more airports right now. So we've got to modernize the airports we already have. We've got to increase capacity at those airports. We've got to preserve access to that capacity, and we've got to build new airports.
These changes bring on not just technological challenges, but social challenges as well. In Japan, airport expansion has provoked sharp opposition over the use of limited open land. But in Denver, Colorado, they want to move the planes away from the people by building a huge but controversial new airport more than 20 miles outside the metropolitan area, with plenty of space for expansion. Bell's XV-15 tiltrotor, testbed for the production line V-22 Osprey, could lead to new ways of getting to the airport, or avoiding having to travel to the airport at all. With new and different types of planes on the scene, air traffic control will become more complex.
Cross 360 Foxtrot one time. Battery 33225.
The system is already outdated and overloaded.
American 278 regional departure.
New tools are urgently needed to deal with this increased volume. In the next 5 years, advanced systems are scheduled to come online to help relieve the pressure.
We've got to take maximum advantage of technology, of electronics, of communications, global positioning satellites. So we have to have a completely a systems approach.
A network of linked computers will help to manage the flow of a national airspace system. Weather systems, too, will encompass a larger, more integrated picture of the country's airspace. These concerns exist not just on a national scale, but rather on a global one. Around the world, commercial flight is feeling the effects of its own success. As demand grows, technology must help to ensure the system's health and continued growth. And with this help, tomorrow's airliner is being shaped. The promise of safer, more efficient, and much faster flight is in the air.